What's up guys, this is Massey. Welcome to another video. In this video I want to talk about application of vector addition. Let's start with an example, which is saying that resultants of rectangular components. Here in this example it says, draw a resultant for each set of rectangular components, then calculate the magnitude and direction relative to the horizontal vector of the resultant. Part A is saying that the sailboat's destination is 8 kilometers east and 6 kilometers north, and they are perpendicular to each other because one of them is going east, the other one is going north. So when we draw it, we keep the vectors head to tail, so the resultant is going to be vector R. And since we are dealing with the right triangle, we can find out the hypotenuse. So hypotenuse based on Pythagorean theorem, we can say it's going to be R, magnitude of R to the power of 2 equals to 6 to the power of 2 plus 8 to the power of 2. That will give me R, magnitude of R equals to 10. Now calculate the angle of the sailboat. So theta, as you see here, if we consider tan theta is going to be opposite divided by hypotenuse. So we can say tan theta equals to 6 over 8, or we can say theta equals to inverse of tan of 6 over 8. That will give us 36.9 degrees. Since this situation involves navigation, calculate the direction as a bearing. So we have direction as a bearing is going to be 90 minus 36.9, which is going to be 53.1. So the resultant displacement is 10 kilometers at the bearing of about 53.1 degrees. Part B. In a numerical model of a Bay of Fundy, the velocity of the water is given using rectangular vector components of 2.5 meters per second northwest and 3.5 meters per second southwest. So we need to find out the resultant vector. So resultant vector is going to be like that. So using the parallelogram method to draw the resultant, and then after that we use the Pythagorean theorem, you can find out the magnitude of the hypotenuse, which is going to be 3.5 to the power of 2 plus 2.5 to the power of 2. The magnitude of R is going to be 4.3. So let's find out the value of theta. Theta is going to be inverse of tan 2.5 divided by 3.5. So that will be 35.5 degrees. Since the 3.5 meters per second vector is 45 degrees below the horizontal, R is going to be just 45 minus 35.5, which is going to be 9.5 below the horizontal. So that's going to be 90 minus 9.5, which is going to be 80.5 west of south. And the water velocity is about 4.3 meters per second. So we can say the direction is going to be south 80.5 degrees west. Now let's see the concept of equilibrant vector. An equilibrant vector is one that balances another vector or a combination of vectors. It is equal in magnitude, but it's going to be opposite in direction to the resultant vector. If the equilibrant is added to a given system of vectors, the sum of all vectors is going to be 0. So all vectors, including the equilibrant, is going to be 0. Let's see the next example. Find the resultant and its equilibrant. A clown with mass 80 kilograms is shot out of a cannon with a horizontal force of 2000 Newton. The vertical force is the acceleration due to gravity, which is 9.8 meters per second squared, times the mass of the clown. Find the magnitude and direction of the resultant force on a clown, and find the magnitude and direction of the equilibrant force on a clown. So we draw a vector on a situation. The vertical force is going to be 9.8 times 80 kilograms, or it's going to be 784 Newton. It's going to be downward. And we had horizontal force of 2000 Newton. And to find out the resultant force, F, let's call it lowercase f, we need to add these two vectors. And the magnitude is going to be the hypotenuse using the Pythagorean theorem. This is going to be 2000 squared plus 784 squared. The answer is going to be, F is going to be 2148 Newton. So that's going to be the resultant of this force. To find the direction of the resultant force, we need to use the trigonometry and say tan theta equals to opposite divided by adjacent, which is 784 divided by 2000. And the theta is going to be 21 degrees. So the resultant has the magnitude of about 2150 Newton and a direction of 21 degrees below the horizontal. Now let's do the part B. Part B, it says, find the magnitude and direction of the equilibrant force on a clown. So in part A, we found out the force is going to be 2150 and it's going to be down by 21 degrees. Equilibrant has magnitude of the exactly the same thing but in opposite direction, which is going to be 159 counterclockwise from the horizontal. Now let's see the concept of heading. A heading is the direction in which a vessel is steered to overcome other forces such as wind or current, with the intended resultant direction being the bearing. So as you see here, we have heading and we have wind or current, and that results in bearing or direction of the resultant. Another concept is going to be ground velocity. Ground velocity is the velocity of an object relative to the ground. It is the resultant or bearing velocity when the heading velocity or air velocity and the effect of wind or current are added. So when we add air velocity and wind or current velocity, we're going to have ground velocity or resultant. Let's see this example. Solve a flight problem. An airplane is flying at an airspeed of 500 kilometers per hour on a heading of 40 degrees. 150 kilometers per hour wind is blowing from the bearing of 120 degrees. Determine the ground velocity of the airplane and the direction of flight. So we need to draw a diagram illustrating the velocities and resultant vector. Use a compass quadrant vector. So we have 500, which is north 40 east, and then we have 150 kilometers per hour wind is blowing from a bearing of 120. Now we need to find out the ground velocity. So the resultant of these two vectors is going to be r. And here we can say, we can use cosine law. R squared equals to 150 squared plus 500 squared minus 2 times 150 times 500 times cosine 80. Answer, the magnitude of R is going to be 496.44. How to find theta? We can use sine law. Sine theta divided by 500 equals to sine 80 divided by R, which is 496.44. Using that method, we can find theta, which is going to be 82.689 degrees. To determine the bearing, translate the resultant so its tail is at the origin of the compass quadrant. The head of the original wind vector is 60 degrees off 180, so the head of the translated wind vector is 60 degrees off 360. So alpha is going to be 82.689 minus 60 degrees. So it's going to be 22.689. The airplane is flying at the ground velocity of about 496 kilometers per hour on a bearing of about 23 degrees. Now let's see the next example. A traffic light at the intersection is hanging from two wires of equal length, making an angle of 10 degrees below the horizontal. The traffic light weight is 2500 Newton. What are the tensions in the wire? So we draw a vector diagram so that the two tension vectors are keeping the traffic light at equilibrium. So we have T1 and T2 represent the two equal magnitude tensions. And we have 2500 Newton downward force of the traffic light is the equilibrant vector. Find the resultant of tensions. So it is going to be something like that. T1 and T2 provides 2500 Newton. So redraw the diagram to show the sum of the vectors with the resultant of 2500 upward, because as we discussed in the previous figure, we have 2500 downward, that's the equilibrant, so the resultant of T1 and T2 is going to be 2500 upward. And we have the equal angles at the base of the isosceles triangle, so it's going to be 180 minus 20 divided by 2 is going to be 80 degrees. So we use sine law. T1 divided by sine 80 equals to 2500 divided by sine 20. So T1, which is equals to T2, can be calculated, and it's going to be around 7200 Newton at 10 degrees below the horizontal. So to wrap up, we have key concepts here. Two vectors that are perpendicular to each other and add together to give a vector of V are called the rectangular vector components of V. When two vectors act on an object, you can use vector addition, the Pythagorean theorem, and trigonometry to find out the resultant. An equilibrant vector is the opposite of resultant, which if you find a summation is going to be 0. Directions of resultants can be expressed as angles relative to one of the given vectors, or they can be expressed as bearings.